Have you submitted the task? All of you? Anyone haven't yet? Okay. After having a lunch, now we will continue to the next session. For the third and fourth session, we are honored to invite Dr. Tjuawinata, who will deliver his lecture on differential cryptanalysis for the third session and multi-party computation for the fourth session. Let's give him applause.
Okay, thank you for the introduction and for the opportunity for me to give this talk. Before I start the session, I would like to first give some short introduction about the research center I'm currently working under, which is SCRIPS. SCRIPS is a research center under NTU, and it stands for Strategic Center for Research in Privacy-Preserving Technologies and Systems. SCRIPS is a multidisciplinary research center that is funded by these two center, which is NRF and also IMDA. And the focus here is just try to find the technology to keep the privacy of your data while trying to maximize the result of the analysis that you can do with your private data. Of course, this is very essential for organizations such as those who want to carry out some data analysis where the data comes from various jurisdictions. For some example, you can imagine that if you want to analyze some health data, then you may want to find some data from the hospital and also from census. Okay, so for our center, we have 3 missions. The first one is to try to develop some technology to be able to help us to preserve the privacy of data while maximizing the use of this data. Next, we want to be able to be the center of knowledge for these privacy-preserving problems. And lastly, we want to, of course, try to improve the theoretical result on these fields. Our center has 3 different sections. The first one is we want to be able to improve the theoretical result in these two parts. The first one is to compute on encrypted data. You may remember from the previous talk that if you have a homomorphic encryption, you can try to calculate based on the ciphertext instead of the plain text. So in here, we will also have multi-party computation, which will be the topic of my next section, and also searchable encryption. The next part is also about differential privacy, which I think you may have heard from Google or Apple. All of this theory is very useful, and we can apply it to our daily life, for example, for e-commerce and also for e-health, which I mentioned before. So for this, we would like to be able to apply our theory here and develop some technology to transfer this to life, and we want to be able to help the government agencies and also industrial partners where we can transfer this knowledge to a product that they can use for this privacy preserving technology. Okay, so this is our role. So we want to be able to help government, industry, and people. Government, we would like to be able to provide this solution so that we can cooperate the different economy. Next, for industry, we would like to be able to be the center of research on these technologies and, of course, provide skilled manpower to apply it. And lastly, for people, we would like to be able to provide some application that you can use that assure some privacy. Okay, so this is just some summary on what we are doing now. Okay, so these are the short introduction for scripts. So let's move on to the differential cryptanalysis. Okay, so for my first session, I would like to briefly introduce this concept of differential cryptanalysis, which is quite a fundamental but very useful method to analyze symmetric key encryption scheme and in particular block ciphers. So this is the overview of my session today. First, I would like to briefly discuss what is block cipher and how to analyze. And having this knowledge, I would like to discuss in more detail about differential cryptanalysis, and this includes background and motivation, how to perform it on one kind of block cipher which is called SPN. And then based on this analysis, we would like to be able to launch distinguishing and key recovery attack. And lastly, I would also briefly discuss 3 different variants of differential cryptanalysis that you will be able to find in literature. Please take note that for this session and the next session, I will just give some very basic idea on the method, and hopefully this one will be very useful for you when you try to read some papers on these topics. Okay, first block cipher, as you may have known, for block cipher, the input of it must be of fixed length, say n. So if your message is not of this length n, then we can use some padding and partitioning to transform it to some blocks of length n. Please take note that for this session today, for simplicity, let's just assume that the message is already of length n and we just ignore the padding and also the partitioning. The objective is to design encryption and decryption function such that it is injective and pseudo-random. So you may remember from before that we need the function to be injective so that we can somehow get back the plain text from the ciphertext. And the next one, pseudo-random, is to prevent any information leakage about your plain text and key from your ciphertext. Okay, we will be working under this principle, which says that for your design, you should assume that everything is known to the attacker except for the secret key. Okay, one of the most commonly used form of block cipher is designed based on iterated block cipher, which simply means that you try to define a relatively simpler function that we will call round function, and then we just call this function for several rounds. Now, you may want to make this round function to be affected by the secret key. So if you want to do this, then in addition to your round function, you will also need to have this key scheduling function that will generate different key for different round based on your secret key, and this will be called round key. So again, for simplicity, for our discussion today, I will assume that the key scheduling function simply outputs back the secret key again and again for the round key. So based on the form of the round function, you may heard of these 2 forms, SPN or Substitution Permutation Network and Feistel Network. And here we will just discuss SPN. As the name suggests, SPN just for each round it consists of 2 different layers, Substitution Layer and Permutation Layer. For Substitution Layer, it is usually designed by using a smaller bijection that is performed. So in here, suppose that you have M that is a divisor of N, then this substitution layer just consists of this bijection of M bits. This smaller bijection is called Sbox, and we will see the example later. Next, for the permutation layer, it's simply a linear layer. So in contrast to substitution layer that is designed to be highly nonlinear, for permutation layer, we just assume that it is linear, and the use of this is simply to make sure that output of each Sbox affect as many Sboxes as possible in the next round. You may have heard example of SPN, which is AES and present. So these are 2 most widely known SPN. Okay, so this is the theory. Let's see some example on how to build an SPN cipher. Okay, so this is a typical example of a round function of substitution permutation network. So let's go from top to bottom. As you can see here, for each wire here, it represents 1 bit. So in our example here, we have 16 bit for our block size. And then this is where the key is affecting the round. So here we simply just XOR the key with the state. Please take note that in case you don't know, XOR is simply just bit by bit addition modulo 2. And then for this 16, we just divide into 4 subblocks, and then we just use this Sbox 4 times for each 4 subblocks. So in here, notice that if we want to be able to go up, that means that this Sbox needs to be bijective. And remember before, it is highly nonlinear. So as long as you satisfy these two, you can use any bijective that you want. Furthermore, if you want, you can also consider to use different Sbox for different subblocks here. But again, since the analysis will be more or less assume that the Sbox is the same for all 4. Lastly, this is the permutation layer. So for our example here, it is simply the reordering of the wire. And you will see that this one can spread the effect of each Sbox to all possible subblocks. Okay, so see how to encrypt using this. So I'll just go through quickly. So first of all, you have 4 subblocks. I use different colors. And you do the key addition. Okay, now notice that in here, for each Sbox, I use different color, and we will see what is the effect of each. And as you can see, for all 4 Sbox, it affects all 4 parts. So for example, if I just change the value of the first subblock, it will of course change the whole block instead of just the first 4 bits. Okay, so the declaration is almost the same, so we start from below. And notice that in here, since the round function affects the whole block at the same time, we need all the layers to be bijective. So that's why earlier we need the Sbox to be bijective. Okay, so up to now we have seen the example of the frame of this SPN round function. Now let's see an example of Sbox. So in this case, notice that Sbox has 4-bit input and 4-bit output. And to make things easy, I'll just assume it can be seen as one integer between 0 and 50. So this is an example of Sbox. As I mentioned, it's simply a bijection. You can choose anything for this one. You can, let's say 6 is mapped to 5 and 9 is mapped to 11. Okay, so now we have all of our components for SPN. So let's consider how to construct this SPN. So as the name suggests, the iterated block cipher, we may want to just do it on top of each other. So this is round 1, this is round 2, this is round 3. So XOR, SP, XOR. Okay, so you may think that since the name is iterated cipher, we can just do 1 round at a time, and this is an example of 3 rounds. However, notice that in here, if I assume that this one is my plain text, and this is my ciphertext, since the attacker knows what is P and S, then he can simply decrypt up to here. So in other words, if I just let this one to be my ciphertext, then the attacker can simply destroy these 2 and just know what is the value in here, let's say state. So because of this, as you can see, if we just stop here, then the last round is useless. So to solve this one, instead of having this to be the ciphertext, we add one more key addition to make the attacker stop here instead of stopping here. Okay, so this is the first observation. For the next observation, as you can see here, for your XOR and permutation layer, both of them are done bit by bit independently. So in other words, actually we can simply flip it, and this one is still the same, of course, with some change of the key. So because of this, again, this permutation layer is actually useless. So if you want, you can simply omit this last P. Okay, so after all of this, then this is the toy SPN that we have. So notice that in here we have 4 rounds. This is the first, second, third, and fourth. And notice that for the fourth one, we don't have any permutation layer, and we just add one more key. So please take note of this SPN, because this will be used for our example later. Okay, so now we have learned about block cipher. Now we see how to analyze it. Okay, so for the analysis of block cipher, it is a bit different from the analysis of public key encryption, because now, since we only have one secret key for encryption and decryption, the attacker does not know this key. So in here, we can still use a deterministic function instead of having to have a probabilistic function. Okay, so recall from before that we want to design this to be pseudo-random or indistinguishable for any random permutation. So if we can somehow find a property of this encryption or decryption that can help us to differentiate between this function and any random permutation, this is considered an attack and called distinguishing attack. Although you may think that it is not so severe of being able to distinguish this encryption with a random permutation, actually it can be used as a base for a more destructive attack that we will see later. Okay, so these are the 2 attacks that is more destructive. First of all, as you may see, as you may have seen in the example earlier, we don't want the attacker to know the value of the state in the middle, because if he can notice, then he can simply cut to 2 and like one of them. So if we can find an attack that somehow gives the attacker the value of some state in the middle, then this is considered an attack, which is called a state recovery attack. And lastly, we also have key recovery attack. Remember that from before, for your design, everything is known except for the key. So if the key is revealed, then everything is broken. Okay, so we will bring 2 different attack models. So again, this is a bit different from the that you have earlier for public key. For chosen plaintext attack, now the attacker is given the chance to ask for Q plaintext that he chooses, and then obtain the corresponding C1 to CQ. Use this to have some information about the ciphers and secret key. Next, for chosen ciphertext attack, it is a bit stronger, because on top of having this Q1 plaintext, he can also ask for Q2 other ciphertext and for the plaintext. So now we are ready to go to differential cryptanalysis, and I will start with intuition. So remember that intuitively, as I've mentioned before, this encryption function E fixing K is supposed to be pseudo-random function. And for simplicity, let's just denote it to be E sub K. Now, since EK is supposed to be pseudo-random, then if you have 2 plaintexts with some fixed relation between them, but they are not equal, then this should not give you any pattern that you can recognize in the output. So in particular, if you have fixed the difference between 2 plaintexts to be gamma, then the distribution of the difference should be uniform, or at least close. So in other words, if you can find some gamma and delta such that this one has the probability of happening larger, significantly larger or significantly smaller than 1 over 2 power n, then this is. So we call this gamma and delta to be the distinguisher on EK. Okay, so differential cryptanalysis was firstly introduced by Beham and Shamir in late 1980s, and it is a chosen plaintext attack. It is chosen plaintext attack because, as you can see, we want the difference of the input to be gamma, so we need to choose it to be equal to gamma. It is actually a very useful analysis. If you read some design of block cipher or even authenticated encryption, you will see that there's some section that a differential cryptanalysis. This one is just to show that it is secure against this attack. And up to now, if you try to find in literature, you will find still there's a lot of possible papers that attacks existing cipher using this differential cryptanalysis or some variants of it. So let's properly define this differential cryptanalysis. As before, we have this function f that we want to analyze, which is f to n to f to n. Pair gamma and delta, both of them non-zero, such that this probability, which means that the probability of the output equals to delta if we make the difference of the input to be gamma, should be significantly larger than 1 over 2 power n. Please take note that in here we don't want to set gamma and delta to be 0 because, of course, no matter what your function is, if the difference in the input is 0, then the difference of output must be 0. So we don't want this to be the part of our analysis. So for simplicity, we just assume that we are attacking SPN, but you can use the same idea to attack a lot other form of ciphers such as Feistel network or even authenticated encryption. So as you may have guessed, the main challenge here is to find this gamma and delta such that it has a good difference. So as you know, for SPN, your function is composed by some sub-functions. So let's say this is F1, F2. So the main idea, usually how we build this difference gamma and delta, is to first analyze each sub-function separately. Suppose that now we have this gamma 1, delta 1, gamma 2, delta 2. Okay, suppose that now we stop at 5. You can just continue to the end. And we have this to have some probability. Please take note that if your function is quite simple, sometimes it is possible to just try to find the best possible difference. However, this may not be possible when you just combine all of them together. So that's why first we just divide into smaller case and try to find this gamma 1, delta 1, and so on with this probability. Now, note that here we don't want to just have the difference in just one section at a time. We want them to link. So to make them link, then we need delta 1 to be equal to gamma 2, delta 2 equals to gamma 3, and so on. So this is what I mean by this one. We need to be able to link. So now, since they are the same, then instead of having these two to be cut, it is now again just a trail from one to the last. So in here, this means that now for this F1, F5, F4, F3, F2, F1, then for this F, we have one difference which is just gamma 1, delta 5. And the probability, assuming that all of these F1 to F5 are independent, is simply the product of all of this probability. Yeah, so if we can somehow make sure that this probability is significantly higher than 1 over 2 power n, then we found one distinguisher. So now, to make things easy, I will just call this chain from gamma 1, gamma 2, gamma 3 up to gamma 5, delta 5 is called a differential trail for F. And note that if we just fix the two ends, gamma 1 and delta 5, actually there's a possibility that you can find another trail. Because of this, actually the probability that you are calculating here is just a lower bound of the severity of your attack. Okay, so now we have our trail from differential cryptanalysis. We will discuss how to use this to launch a distinguishing attack on SPN. So before we do that, let's try to first define how to do this distinguishing attack in general. So the main idea here, as before, we want to be able to distinguish between the function that we are analyzing, f, from a random permutation pi. The attack is in the form of a game like before, where attacker is provided some unknown function g, which can be either f or random permutation pi, and he can do a lot of things with it. So for example, in this case, we have the choice of some chosen plaintext and asked to find what is the map of that plaintext out of this G. So the power of the attack here, again, as before, is just the probability that we win the challenge. So in other words, it's just 1 minus the probability of false positive minus probability of false negative. Okay, so let's see how we can do this on differential cryptanalysis. Suppose we have a pair gamma delta like before, and the probability is P, which is much larger than 1 over 2 power n. Then we can collect m pairs of plaintext pi0, pi1, and such that this difference is gamma, and then we ask to find what is Cij to the challenger. Now, after we have all of this Ci0 and Ci1, we find this number n, such that this number represents the number of I, such that the difference of the output is delta. Based on this n, we can then perform a hypothesis testing to check whether large enough. Okay, please take note that in here, for this n is actually a random variable, and you may be able to guess that this follows a binomial distribution with m trials and success E if G is f, and if G is pi, the success probability is 1 over 2n. So there are two remaining questions that is not answered up to now. First of all, what is this m? And secondly, when is n large enough? For the first question, actually, it can be shown that if you pair gamma and delta the p, then this is said to be c over p for some small c. Again, we will see this in the example later. Next, how large is n? So you may remember that in here we want the probability of error to be small, and we have two errors. The first one is the false negative error, and the second one is the false positive error. Of course, we want these two to be small. So suppose that one way to do it is just to bound the probability of false negative to be this alpha for some small alpha that you set. In other words, now we just such that the probability of x is less than a is less than or equal to alpha, given that x follows binomial distribution with m trials and success probability p. Again, this one you can write a simple program to find what is A, or if you want to make it simpler, or if it is just too large, you can also consider to use normal approximation here. So this is an attack. So let's see some example on our toy SPN earlier. We will consider only 3 rounds instead of 4, but you can also try to find a similar attack on 4 rounds. Note that there are 3 parts that we need to consider. First is the Sbox layer, permutation layer, and the key addition layer. Now, for the key addition and permutation, note that both of them are just linear functions. So we will just consider them together, and in fact, we can prove that any key addition can be ignored, and we will see later why it is. On the other hand, Sbox is designed to be highly nonlinear, and we will discuss them separately. Okay, so first of all, suppose that F is linear. By definition, this one means that you should be able to find an n times n binary matrix A and binary vector B of length n, such that Fx is just equal to Ax XOR B. So if X XOR Y equals to gamma, you can simply expand everything and see that Fx XOR Fy must be A times gamma. So this one tells us that this probability is only either 1 or 0. 1 if delta equals to A gamma and 0 otherwise. So for every permutation layer or key addition that you find, you can just change this delta to be A gamma and you will have probability 1 and you can simply ignore it. Notice that this also means that for your key addition, since the key addition is simply Fx equals to X XOR K, then we don't need to change delta from gamma, so delta equals to gamma and the probability is still 1. So this is why I mentioned earlier that you can simply ignore every key addition in the middle. So next, for nonlinear layer. So remember that for your substitution layer, it consists of 4 different Sbox. So first we need to consider each one separately. And notice that in here for your gamma, delta, and x, it can only be from 0 to 15. So since there's just a small number of it, you can simply write a short program to find the probability. Okay, so this is the result of what you will get if you try to find the probability for all possible gamma and delta for your Sbox. So for example, this one means that if you give the input difference to be 4, then the output difference will be 7 with probability 3 over 8. Now please take note that in here, apart from this one, all the other non-zero is strictly less than 1. So this means that for any Sbox, if you introduce non-zero difference to it, then you can only do it with probability less than 1. So this gives us an that we don't want to have many Sboxes with non-zero difference because it will just make your probability lower and lower. Furthermore, you may remember from before that the permutation layer will spread your output difference of the substitution layer to all 4 different Sbox in the next round. So in other words, we want the number of non-zero bits of the output to be as small as possible. So for example, in here, although for 4 to 7, the probability is 3 over 8, and for 8 to 5, the probability is also 3 over 8. We prefer this one rather than this one because 7 has 3 non-zero bits, while 5 only have 2. Okay, so now here, please take note of these 2 differences because this will be the only thing that we will use to construct our trail later. Okay, so these are just everything that I just said earlier. So for the non-zero input difference, we will call it active Sbox, and we want this number of active Sbox to be as low as possible. Okay, so let's try to construct. So please take note that the differential trail that I give here, it's not necessarily the best one, but it will be good enough to launch our attack. Okay, so let's let's introduce 0 difference for the first 3 Sbox and difference of 8 in the last Sbox. So in other words, we only have 1 bit difference in the top wire. So as you may remember, if the input difference is 0, then the output difference is 0 probability 1. So this one we can pass through with probability 1, and the first part 8 goes to 5 probability 3 over 8. So now in here, the non-zero bit will be the first and the third one of the top Sbox. So this will introduce a difference of 8 in the first and third Sbox in the second round, while these two are still 0. So again, we can simply use the same thing as before. For 0, it goes to 0 probability 1, and 8 goes to 5 probability 3 over 8. So again, we can simply change this, the first and third goes to this one and this one, the same thing for here. So you will introduce of difference 5 in the first and third, and the second and fourth, it will be 0 again. Okay, so this is where the difference of 5 can go to 10 with probability 1 over 4, and lastly, this gives you 0.505 at the output. Okay, so this is the one example of differential trail. So you start with 0008, and then in here it becomes 0005. Here becomes 8080, and so on until the output difference becomes 0505. Now, how to calculate the total probability? Notice that everything here has probability 1 except for these active Sboxes 1, 2, 3, 4, and 5. So in other words, the probability is simply the product of the probability of all of these active Sboxes. So we have created this differential from 0008 to 0505. And the probability is 3 over 8 power 3 times 1 over 4 power 2, which is 216 over 2 power 16. Now please take note that in here, since your block size is 16 bits, that means that if it is a random permutation, then this differential will have probability 1 over 2 to 16. So in other words, in this case, actually we have the probability to be 200, at around 200 larger than the random permutation, and we hope this is enough to launch the attack. So next step, how to find a distinguishing attack based on this. Suppose that now we are given a function f, and we need to guess whether it is a random permutation pi or 3-round instance of our SPN cipher, and let's denote it by E. Now remember that we want to test out this differential, so we just collect m different plaintext pairs pi0, pi1 with difference 0008, and we don't want to repeat so that we can have as many samples as possible. Now, based on this requirement, you may notice that actually this m it be larger than 2 to 15, which is around 30. However, remember that from before, m should be around c over p, where p is this 2 to 16, 216 over 2 to 16. So in other words, c over p is around 304 times c. So if we set c equals to 4, we can try to use m equals to 1216. We will use 2432 plaintext in our attack. Okay, so like before, we just defined this random variable, which is the number of I such that the difference of output is 0505. Then n follows binomial distribution with m trials and 2 possible success probability. If f is E, it is 216 over 2 to 16. If f is pi, it is 1 over 2 to 16. Okay, so remember the strategy here is to find cutoff value such that we will guess f is E if n is larger than p, and we will guess it is pi otherwise. Now, in here we have 2 different probability of error, false positive and false negative. So false positive is just that the probability that this n is larger than p, although f is actually random permutation. And this is just a formula. The same thing for false negative. this probability that F is E, but N is less than P. So again, here you can use random approximation, but for my case here, I just write a short program to find out for different P, what is this alpha and beta. Okay, as you can see here, if M is 1216, then if I set P equals to 1, then the probability of error for both ways are around 2%. And if we push 1 to be small, for example, alpha needs to be small, then beta will increase to be large. So another question here is whether we can do better when we increase M. For example, M 10,000, which is still possible because we have up to 30,000. In fact, it is much better because now if M is 10,000 and P is 8, then both probability is 10 power minus 5%. So this is one example of how you can launch a distinguishing attack based on differential cryptanalysis. Before I go on, any questions? No. Okay, so now how to use this as a base to launch a key recovery attack. So here we will be using the same differential trail as before for 3 rounds, but we will use it to launch a key recovery attack for 4 rounds. So the main idea here is if we are in the 4th round and we can somehow find the key at the last round, then we can simply partially decrypt it until the beginning of the end of round 3. So we can try to guess and then see what happens in the beginning of round 3. So now, if our guess is strong, then the remaining cipher should behave like a random mutation. However, if our guess is right, then the remaining cipher will just be E like before. So in other words, we can simply use, before we first start with M plain text pair with difference 008, and we just record all the possible ciphertext pairs. Now remember that for all the ciphertext, for our differential trail, after 3 rounds, it is expected to be 0505. So in other words, the only non-zero difference is in the 2nd and 4th. And this one corresponds to the difference in the K1 and K3. So we can simply try to guess all of possible K1 and K3, which gives you 2 to the power 8. And for each guess, we partially decrypt and see what is the difference between SI01 and SI01, SI03 and SI13. And we count how many is 55. And remember, if our guess is correct, then this number should be large, otherwise it should be smaller. So for the biggest possible n, then we will guess that this K1 and K3 is the correct guess. Assuming that our guess is already okay, that means that now out of the 16 bits, we already know 8 bits. So the other 8 bits, we can just try 1 by 1. So in this case, your complexity will be 2 power of 8 plus 2 power of 8, which is 2 power 9. This is much better than if you just try all possible key, which needs 2 power 16 of computation. Okay, so this is the end of differential cryptanalysis, and I'll just give some description of 3 different variants of differential cryptanalysis that you may have found from the literature. First of all, for truncated differential, okay, so you may remember from before that this is the form of our SPN. And for the normal differential cryptanalysis, we need to give the actual difference for each subblocks. However, for this one, you may not be able to find one that has a good probability. So one way to improve it is just, instead of having the actual difference, we just specify which block has any difference. For example, we just consider that this tree cannot have any difference, and in here it has some non-zero difference, and we will just consider all possible difference there. So of course this one will increase your probability, and this can give you some distinguishing attack. Okay, for the next one, for the impossible differential, remember that from before, we want the probability to be very large. In here, it's the other way around. We just want to make the probability to be 0. Now remember that for random permutations, assuming that it is uniformly random, then any possible output difference should happen, and it should not happen that we have 0 difference here. So again, this is one way to differentiate. Lastly, for the boomerang attack, you may remember from before that if we have the function to be a composition of 2 different functions, and then we have this gamma 0 delta 0 difference here and gamma 1 delta 1 here, then for us to be able to launch this differential attack, we need this gamma 0 to be equal to delta 0 to be equal to gamma 1. So the remaining question is, what happens if we cannot find this to be the same? So this is how boomerang attack comes. So the main idea here is, instead of having just 1 pair, we will be using 2 pairs. Now suppose that now our function that we want to analyze is E, and it can be divided into E1 and E0. And suppose that for EI, it has differential gamma I, delta I, gamma, with probability Pi. So instead of just combining everything together, we start with 2 P0 and P1, and notice that after E0, if this one has difference gamma 0, then the output S0, S1 is delta 0 with probability P0. Now if we add E1 here, then we don't really know the difference between C0 and C1 because we don't have any differential of E1 with input difference delta 0. So instead, we just give a difference of delta 1 to C0 and C1 to get C2 and C3. Okay, so after this we have these 2, then we use this ciphertext and ask for the plain text. Okay, so now in here, notice that in here I forgot to mention, although I write this S0, S1, S2, S3, in reality we don't know what is this. We only know P0 up to P3 and C0 and C3. So this one is just to help us to perform our analysis. Now notice that in here, since the difference here is delta 1, then based on this difference, then the difference here is gamma 1 with probability P1, and this one also have difference gamma 1 with probability P1. So in other words, in here, with probability P1 times P0, or P1 squared times P0, this S2 XOR X3 equals to S2 XOR S0. And notice that in here, we already have here, the difference here is gamma 1 with probability P1. This is delta 0 with probability P0, and this one is gamma 1 with probability P1. Okay, so with this probability, then this difference is delta 0. So we know we can just use this E0 again to have that this is probability with probability P0 square, P1 square, this difference will be gamma 0. Okay, so this is why the name is Boomerang Attack. We introduce difference gamma 0 here and hope that it can come back to gamma 0 in the second pair. Okay, so as you can imagine here, since now we ask for the encryption of P0 and P1, and we ask for the decryption of C2 and C3, now this one is now a chosen ciphertext attack instead of chosen plaintext attack. Okay, so that's all that I want to say for the first session. Thank you.
Thank you very much, Dr. Ivan Tjuawinata, for the lecture on, still remember? Okay, differential cryptanalysis. Okay, even we still have 30 minutes before coffee break, but it's okay. Yeah, maybe we can start a coffee break from now, but we will continue the fourth session at 3 or at 3:30. Okay. 3:30. At 3, okay. Okay, at 3. Okay, enjoy your time.